Welcome back to the Tailosive Tech Podcast. I'm your host, Nick, and today we have a very special interview. I've been looking forward to this for quite a few months now. I actually got on the line Michael, who is a literal spacecraft test pilot. He has probably the coolest title I've ever heard, and he also has a pretty fun job, too. So how are you doing, Michael?
I'm doing good. Thanks for having me on.
Yeah, thanks for coming on. This is going to be fun. I'm looking forward to it.
Yeah.
So first off, what do you do? Like, walk me through this.
So I am a spacecraft test engineer, and so basically my job is to integrate a full-up spacecraft and test it all the way through to launch. And then after launch, I will usually hang around and do operations and commission the spacecraft and get it up and running.
Wow, that's pretty cool. So what does testing it look like? Like how do you test a satellite that is designed to work in space?
Yeah, there's several different phases of kind of what we call integration and test. And so you start off in the integration phase where you're kind of collecting all the parts that you have ordered during the design phase. And so you're now putting it all together. So you're taking all the avionics, all of your sensors, all of your, prop system, so your thrusters, your reaction wheels, all of those components, and you're plugging everything in with the flight harness, and then you're making sure that everything's working as designed and expected. And that's kind of the integration phase. And then you move on into performance testing. And so now you're looking at the whole spacecraft as a system, and you're making sure that the system works together. And that they're, when you send a certain command to flight software, that it then goes and, turns on a switch or, starts running one of the wheels in a certain direction or fires a thruster. So that's kind of your performance testing phase. And then you move into what's called environmental testing. And that's where you actually put the spacecraft through its paces of what it's going to see during launch and then when it's on orbit. And so we'll do what we call EMI, EMC, electromagnetic interference testing. And so basically you bombard the spacecraft with a bunch of different signals and make sure that, everything still works. And then you also kind of turn everything on, and then you listen for signals coming off of the vehicle and making sure that nothing's interfering with the rest of the spacecraft. So you don't want to have like reaction wheels spinning, and that's messing with one of the instruments that's supposed to be taking, photos of Mars, which is kind of my current spacecraft I'm working on. You don't want there to be interference. You want to make sure that the spacecraft will function, and then it will also be able to gather science. And so that's kind of what environmental testing is. We do, EMI, EMC. We'll do a shock test to make sure that when it comes off of the launch vehicle.
They shake it?
That's vibration testing.
Okay.
Shock is actually when you come off of the launch vehicle, you want to make sure that the whole spacecraft's going to survive that, because that's actually kind of a big jolt.
Okay.
And then you have vibration testing where you actually put it on a shaker table and you shake the whole spacecraft and make sure that nothing comes apart, nothing falls off or falls out of the vehicle. So that's a pretty important one. We have acoustic testing. So we actually get a bunch of speakers from, we usually use Maryland Sound. They're a company that puts on big rock concerts. So we take these massive speaker stacks and stack them all the way 360 degrees around the spacecraft. And then we play sounds like a rocket launch. And so we kind of get that frequency going, and we make sure that the spacecraft will survive the sound and the vibrations of launch. And then kind of the very last big test, environmental test that we do is called Tvac. It's thermal vac. And so we actually put the spacecraft in a giant vacuum chamber, suck all the oxygen out, and then we ramp temperatures really warm and really cold. So what it's going to see while it's out in space. And we make sure that it functions. And so we run a bunch of performance testing while it's in that state. And we just ramp it hot and cold a couple times to make sure that everything works. So that's kind of that's your environmental testing phase. And then after that, you kind of do another performance test, and you make sure that it has survived all the environmental testing, that it's good to go. And then you ship it off to the launch base, and you do some more testing to make sure that it survived the trip, and then you bolt it to a rocket and light the jets, and off it goes.
With all what you just described, the launch sounds like the simplest part of the mission.
It's pretty simple. There's not a whole lot I can do during launch, right? It's like make sure the spacecraft's ready and then hope that the launch provider has done all their testing and that it's good, so that when they actually, light the candles, the thing isn't going to explode or not make it to orbit. And so, yeah, there's a bit of trust there that, you kind of have to let it go, right? It's a scary, tense moment when you've spent years working on something and now it's on a giant bomb and you just hope that it works.
Hope that all the explosion goes in one direction.
Exactly, yes.
So basically your job is to find out every single variable and account for that, or are you just specifically making sure the thing works?
Yes. It's kind of the short answer there. We spend a lot of time thinking through everything that we think could go wrong and what we actually need to test, and where we think the failures will be, and that's kind of where we push our testing towards to make sure that everything works. It's a balance because you have schedule pressure, you have price consideration, how much you're actually getting paid to do this. And so you have to kind of balance all of that to figure out what your test program is actually going to look like. And you want to focus on the things that are most likely going to break, and you want to make sure those are rock solid.
Wow. That's an exciting job. So right now you're working on the Hope Mars mission, right?
That's correct, yes.
And you've kind of been helping them because their launch is in July
14th. Yes.
I'm sure you've had that date circled on your calendar for a little while.
Oh yeah. We have a whole countdown going and all that fun stuff. Yeah, it's coming up quick. It's exciting. like less than 2 months now.
That's crazy.
Yeah,
and it'll be a little bit closer after this episode airs. But and I was reading a little bit about the mission, and it looks like if the launch provider misses that window, you guys are going to be waiting for 2 years, right?
That's correct. Yeah.
That's insane.
Yeah.
Like, just be that precise and have that tight of a deadline, now or never.
Yeah, I mean, this has been a firm launch date since I came on the program, and it's like we have to hit it, and we've kicked butt and gotten to the point where it's going to happen. So
that's awesome.
Yeah.
So what other programs have you worked on, or been involved with any other projects?
I have. This is actually, I believe, my 6th spacecraft that I've worked on. Couple of the other ones I've worked on, Digital Globe, which is now owned by Maxar. They had a series of Worldview satellites. I don't know if you've ever heard of the Worldview satellites.
I think so. They have like a couple, like a dozen of them, right?
They have 3 big ones, and then they kind of they bought another company, and then they which came with more spacecraft, and they're working on a whole nother set of building the next generation basically. But they're the satellites that take all the kind of Google Earth and Google Maps satellite photos, and they get those from Digital Globe. And so I worked on Worldview 3, and then I worked on 2 weather satellites, NPP and JPSS. Both of those, are still flying and providing a lot of weather data. If you see a lot of the really cool images they take, where you see you see the United States, and then you see all of the clouds and stuff that are flying over. Those are usually from JPSS or NPP, and they take pretty awesome photos. Those are big lumbering spacecraft. They were this wedge shape, and the whole top deck was like 5 different weather instruments on it. And so there's actually
weather radars and optical stuff, or spectrometers, or what kind of stuff do they put on those?
Looking at clouds, looking at infrared, looking at visible light frequency stuff, trying to gather all that, and then they correlate all that. Really cool. Fun way to kind of get my hands dirty. That's back when I was actually a spacecraft technician. And so as a technician, I did all the hands-on work. So I actually...
So you're one of the guys in the white suits?
Yeah. Yep. So I was actually,
That is so cool.
yeah, I was actually bolting on all the boxes and putting everything together. And there's actually, I'll have to dig it up and send you a link, but I have a link where there's photos of me actually putting the instruments onto the JPSS spacecraft. They're all on NASA's site. And so really cool stuff.
Cool.
Yeah. And then
You've touched things that are flying above our heads right now.
yes, yeah.
In orbit. Oh my gosh, that's crazy.
And so those are the unclassified stuff that I've done. And then after that, I kind of moved into the classified arena, and I did a bunch of national defense spacecraft that I definitely can't talk about.
Don't want to do that.
No.
Don't need anyone getting in trouble here.
Yeah.
Yeah,
But
well, that's
those
so
are fun.
fascinating. My goodness.
Yeah.
So are any of one of those more interesting, or do you think like this Mars Hope mission is probably the coolest? Like, you're sending something to Mars. That sounds probably a little bit cooler than a weather station.
Yeah. So when I got recruited to come over, Mars was a big selling point for sure. Getting to not many people get to do a Mars program, and so I was like, yeah, sign me up. Let's go do this. And this program is really unique because we're actually, we're partnered with these guys, and we're teaching them so that they can go off and do it on their own. And it's been a really
cool.
good partnership, and they've been really good. We've gone out to Dubai a couple times to help get them ready for the spacecraft coming through, and then I actually went out there when the spacecraft was there and helped them do some final testing. And and they're super awesome guys. They're learning a lot, and they're taking a lot in, and it's been a really fun program to work on.
That's great. I'm looking forward to this mission. Like, from what I can tell, like this is the first object that the UAE is sending over to Mars, right?
To Mars, yeah. This is their first one. They've had a couple other
crazy.
spacecraft that they've put up in orbit. Khalifa is one that actually takes photos, and it's working. I've been in their control room and watched the photos get downloaded and taken, and it's really pretty cool. They're doing amazing things, and they have a whole 100-year plan. They're thinking way farther ahead than anybody else, and
that's crazy.
Yeah.
So your current job is testing things. Is there anything that's more fun to test or more fascinating to test than others? Are there boring tests, or all of them exciting? How does that work?
They're all kind of exciting. Some of the easy stuff, a lot of the power subsystem is pretty simple. Power on, power off. Are the solar arrays working? That's pretty simple stuff.
How do you test those? Do you take those outside, or?
No, we actually just shine big halogen lights on it, and we're able to pick up the power generation coming off of it. And pretty simple.
That makes sense.
Pretty simple. Those, it's still fun to test, but they're not as cool as kind of my focus has been on this program has been our ADCS system, attitude determination and control system, which is actually flying the vehicle. So
that's very important.
Yeah, it's making sure the vehicle points and moves, and can point at the sun so that the arrays are getting juice coming in. So ADCS is one of my kind of primary focuses, and then my main focus is fault protection. And so fault protection is basically having software on the vehicle that is watching for problems that could occur. And when a problem happens on the vehicle, it autonomously, if I can say that word correctly, takes action and safes the spacecraft so that it doesn't go out of control or we lose communications with it. It takes over and puts it into what we call safe mode. And so most of my testing has been this fault protection testing, which means I get to break the spacecraft and see how it responds. And so I throw faults at it all day. That's my job. I'm going to go break this today and see what the spacecraft does. And that's what my job has been. And it's a really fun job.
And you do that in a simulation or the actual hardware?
Yeah, so we have a whole simulator. So basically we plug in the spacecraft into this simulation environment, and we fake it into thinking that it's actually flying. And so we have a bunch of different scenarios. We have like a launch scenario. We have a Mars orbit insertion scenario. We have what's called the science phase scenario, and we put it into this simulation, and it thinks it's flying, and then we throw faults at it and see what's going on. We make sure that everything's, all the components are working, and that, as it's spinning one wheel, it actually moves. And we have a full 3D view of the spacecraft with, Earth in the background or Mars in the background. It's actually in the right spot in time and space. We can move it to wherever we want for all of our testing. So we do a lot of our testing in the future, right? Because we actually move time and position and velocity of the vehicle to where we think it's going to be for launch. And then we run a launch scenario as it's coming off of the launch vehicle. And we have a full up simulation, and I get to watch, and I can sit there and watch what the vehicle's doing. And I can actually, I've gotten so good that I can diagnose what is wrong with the spacecraft based on how it's flying. So I can just look at how it's flying and tell you, okay, that this component is broken right now and we need to go fix it.
That's crazy.
Yeah. Yeah, it's pretty incredible. And this whole program has been ground up for LASP, and they've done an amazing job, like bringing all of our ground support equipment up, getting the simulations working. It's pretty impressive what we've done.
And in my mind, like you watch SpaceX, launch a bunch of Starlink satellites or whatever, and I don't know, I just think they're satellites, but I'm sure that they're going through very similar testing to what you guys have to do, and simpler hardware or whatever. But there's so much work that goes into these things that I don't think people quite realize that. Like, behind the launch, there's probably 3 or 4 years behind even some.
Yeah, so
internet satellite provider.
At least 5 years. Yeah, you have to. It's 3 years of integration and test, and then it's 2 years of design on the front end of all that. It's a lot of work. And I don't think a lot of people fully realize what it takes to get one of these things ready to go fly.
Yeah. And so you're not doing this all by yourself, I'd assume. You probably have a team.
Yep.
How is your job a team effort? And do you have lots of team input, or how does that work?
Yeah, so this is kind of right now we're a very small team, and we have basically subsystem engineers that actually did all the design and, procured all the parts and got everything going. And then as a test engineer, I get paired up with the subsystem engineers. Okay. And we then go and determine, okay, this is how we want to test it. And then I go and I write all the test procedures and help them verify that the way that their system is designed is going to work properly. And so that's kind of the handoff here is I'm helping them test their system that they designed. And, you
get to go break someone else's work.
Yeah. Yes. Yeah. I get to go and push on it. Okay. Well, let's see if you did this right. You go press here and nope, this isn't working properly. We were supposed to get into Mars orbit, yet here we are crashed on the surface. What happened? What's wrong? That's happened several times. So
I'm sure as a test engineer, you've read up on the Mars Climate Observatory that had a small loss of mission and loss of spacecraft back in the 90s. Yep. Do you guys keep that at the forefront of your mind? The past mistakes that have been made, or are those kinds of all just figured out at this point?
No, we're always thinking, especially from the fault protection mindset. We're thinking, okay, what could go wrong, and how do we protect ourselves or protect the spacecraft from basically dying. That's what it's all about. Let's keep this thing alive. And we really spent a lot of time thinking through all of this stuff and testing, and that's really where you get your confidence is the testing. And so, we'll make a change and then we'll go and test, and then we'll verify that, okay, that change worked and it did as what we expected and it didn't affect anything else. And so there's a lot of that constant iteration. It's like, okay, we made this change. Now let's go retest and make sure that change did what we expected and didn't hurt anything else. And our mindset is very much keep the spacecraft alive, and that's always at the forefront.
Interesting. And just all the redundancy levels that we don't get to see.
Yeah,
I'm sure there are quite a few of those.
There's definitely a bunch of redundancy built in. It's an interesting design. A lot of spacecrafts are dual redundant. They have full redundancy. They'll have two of everything in case one of them fails. They can switch over to the other one. Ours is not that robust, but a lot of the components that it has have redundancy built in. And so if something were to go wrong, we would be able to switch over to kind of a backup system and hopefully be okay.
That's pretty smart. Well, you sound like a pretty smart guy. How did you get started in all this? What day did you wake up and say, you know what? I want to fly spacecraft for a living?
Well, when I was getting out of the military, I was in the Marine Corps for 5 years. I was a systems troubleshooter.
Thank you for your service.
Oh, thank you. I appreciate that. Yeah, I was a systems troubleshooter, and so as I was getting out of the military, I was deciding, okay, I want to go to school, I want to go to college, and as I was getting out, my dad, who works at Ball Aerospace, was able to kind of pass my resume in, and they needed help in their ground support equipment lab, basically. And so they offered me a job, and I started working there. I started going to school, and I kind of just got addicted to it. Working on flight hardware it's fun. It's, how many people get to actually, put something together that then goes up into space. There's just this mystique to it. And, growing up, I loved all of the space stuff. I've been an aerospace nut for forever, since I was tiny. And so just being able to work in this industry and really kind of affect it, and it's been a lot of fun.
Yeah, I can imagine. What kind of schooling did you do? Are you in math or what engineering degree? What kind of degree gets you into this field?
Yeah, so my degree is actually a data science degree. It was kind of interesting. I've always also been into computers and stuff, and I kind of just started working towards. Originally, it was programming, computer engineering, and some of that high level code stuff was pretty out there for me. So I kind of changed my path into more of, looking at large sets of data and all of that. And that's kind of where I went into school for. But, as I got deeper and deeper into the aerospace world, I've just kind of been working that. CU's nice, because LASP is part of the University of Colorado. I'm able to go and take a lot of their classes and stuff as an employee. So I'm in a lot of, I can go and do systems levels classes and kind of learn more of the aerospace stuff that I need to know on kind of their dime, which is nice.
That's great. Love it when you can work that out.
Yeah.
What kind of technology is changing for you guys? Like, is there a big wave in augmented reality type? I don't know. What is there any like fun and innovative technologies that are moving towards the test environment or?
Yeah, so there was actually one thing that I was testing back when I worked at Ball Aerospace. They were starting to do virtual reality, and they were taking spacecraft models and stuff that they had designed in CAD, and they put it into 3D. And I could actually go and like step inside of the spacecraft and walk around the spacecraft and look at all the different components and look at how they were going to route all of their wire harnesses for the spacecraft. And I was able to point out a bunch of stuff that wasn't going to work. I had a lot of hands-on experience, and I put the VR headset on, and I'd go and be like, well, what you guys are doing here isn't going to work. You don't have enough length here, or this, you can't go around this thing. And so I would actually mark up in virtual reality, like, this isn't going to work. You need to do it this way. And I would actually draw all this stuff out for them. And then they would take that feedback and they'd go in and change the design so that it would actually work in real life. So being able to do that virtually before you actually built any hardware saves you time and money in the long run. And so that was kind of one of the the big things that I noticed that they were starting to get into.
That's fascinating. Like if you needed to change something, after you've already built it, you could probably, I don't know. I'm just imagining like a spacecraft. You could take it apart virtually and like switch parts out and stuff, and know the most efficient ways to do that kind of stuff. That's real interesting.
Yeah, and they were thinking ahead. Let's get the guys who are hands on in there to look at this and see if it's going to work.
And that probably saved a few design iterations.
Yes, yeah, hopefully. And it's always better to find it early than later on, because later on it's a lot harder to change. We've run into issues where this harness just isn't quite right. It's not long enough, and I don't know how you messed up the measurements, but this doesn't work, and then it starts a whole rework cycle and takes time and money and schedule.
So if you were talking to a high school, college student who wanted your job, are there any shortcuts that you'd recommend them? Do this or do that, or don't do this and don't do that?
Your best bet is probably like an aerospace, go into aerospace engineering or electrical engineering. Those are kind of the two biggies. There's also systems engineering is another good one. Systems engineering, you kind of get to see the whole picture and kind of focus on bringing all of the small pieces in together to build the full up spacecraft. So those are kind of the routes that I would take. I'd probably, if you really want to understand like how to fly a spacecraft and a lot of the orbital mechanics stuff, aerospace engineering is probably really the way to go.
Interesting. Or just watch Scott Manley for a few hundred hours.
Yeah, there you go.
Pick up some stuff from Kerbal Space on that.
Yep.
So how do you actually fly an interplanetary spacecraft? Do you have a joystick? Is it with?
It's actually with basically code. So we have these sequences, which are just a bunch of commands with timing in them. And so for launch, for example, we have an initial on sequence, and that basically turns on the spacecraft and configures everything so that it can go off and fly. And it does it autonomously. And so it's really a lot of sequences that are driving all this. And so we'll load up the sequence to the vehicle, and then we'll say, okay, start it. And it'll go and it'll start doing its stuff. And there's a lot of talking to navigation and the operations team about what they actually want to accomplish, and then they go and write these sequences so that they can get uploaded. And it's all we have a basic command set for the spacecraft, and it's this huge database of all the different commands that you can send and you kind of what they do, and you sit there and you send commands, and that's what the sequence does, is send commands to make the spacecraft do its thing. It's a flying robot is what it is.
So how do you deal with the time delay? Because as the spacecraft gets closer to Mars, the time delay is going to increase. And then once you're in Mars's orbit, the time delay is going to move to, 45 or 90 minutes or something like that? How does the spacecraft deal with that?
Yeah, so again, this is kind of where you really lean on those sequences. Those sequences have timing built in, expected time in the future. And so it'll do a lot of waits for, okay, wait for it to be this time. And now go and do this, because we know that at this time you're going to be here, or we expect you to be here, as long as you don't run into any issues. And you just rely heavily on a lot of that planning, a lot of that navigation, and those sequences are what drive everything.
And if something were to go wrong, hopefully it doesn't, you obviously have systems on the spacecraft, though, to try to handle some of that. That's what you're talking about before, right? You wouldn't have to wait for a round trip.
Correct. Yeah. The spacecraft is pretty autonomous. If it, we have fault protection, and if it detects a fault, it'll go into what we call safe mode. And safe mode kind of strips everything down. It shuts off the instruments, and it points at the sun so that it's constantly getting power and charging the battery. And it sits there and kind of it waits for us to intervene. It says, okay, I've had a safe mode entry. Here's the code that I'm throwing that I think is wrong. Here's what I saw that was wrong, and this is why I'm in safe mode. And then we download that information, and then we go and determine, okay, well, this is, we lost a reaction wheel. It just died. So now we have to go into the system and take that reaction wheel out so that it's no longer involved in all of the flying algorithms. We don't want to be trying to send commands to a busted component, and so we kind of take that out of the equation. And so we'll reconfigure the vehicle so that it'll fly still. We have redundancy built into the wheels and other components, and so you're able to remove some of those from the algorithms so that it can still fly. And
interesting.
Yeah.
So you have more than 3 reaction wheels.
Yeah, there are 4 reaction wheels on this vehicle.
Huh. What orientation is the 4th one in? How does that work?
It's in basically a square around the instrument deck, and so
okay.
It allows us for really good pointing of all of the science instruments, and that's really what you want. You want to be able to get a good fine point on Mars for those instruments so that they can gather their science.
What kind of scientific payload is the Mars Hope orbiter carrying?
So there's 3 instruments on there, and they're all, so we have like basically a visible camera, we have an infrared camera, ultraviolet camera, and they're designed to basically look at Mars climate and weather and kind of learn more about, why did Mars suddenly become kind of a dead planet, and that's their contribution to the science community is, hey, let's go and look at climate and weather at Mars. That nobody else has really done that.
Huh. That's cool.
Yeah.
So how would they extrapolate that kind of data out of an infrared picture? Would you know much about that, or is that?
That I don't know. That's black magic to me. That's yeah.
Okay, good.
They have some processing tools that are able to figure that out, and scientists who are much smarter than I go and look at that data and can figure stuff out.
So no piece of software is perfect, unfortunately.
Mm-hmm.
What happens if there's a big software glitch besides going into safe mode? Like, is safe mode like the catch-all end-all? Like, I don't know. That sounds scary. I wouldn't trust my phone to work for 2 years straight.
The nice thing about these systems are they're very simple. A lot of this hardware is very, very simple. It's not nearly as complicated as an iPhone. It's all pretty dumb, I guess is kind of the way to put it.
Designed for a specific purpose.
It's designed for a specific purpose. It's designed to be very simple, and you hope that it won't fail. It's all very robust, and yeah, it's you design for the environment you're going into, and you keep it simple.
That's probably pretty smart. Are there a bunch of like error margins, or I'm sure you guys have thought through, what's our margin for the orbit insertion burn, or you probably have some margins built in, right?
Yeah.
How are those defined, and how do you come to those?
Again, this is going off into the the navigation guys and the ADCS guys who they know that stuff, and they go and they look and like, okay, this is where we need to start our burn to get into orbit. We need to burn for this long to slow the vehicle down to get captured by Mars orbit. And then, you take that, your perfect scenario, and then you build margin around it. Well, if we don't start till here, are we going to be okay? And you kind of build those margins around that.
Interesting. Now, how does designing a unmanned spacecraft differ from designing a manned spacecraft? And can you imagine, like, how does the complexities multiply?
Yeah. So I don't have a whole lot of experience with manned space hardware. I did work on the Orion flight computers early on when I started working at Ball Aerospace. And I'll tell you one of the big differences between that being manned hardware and unmanned hardware. The manned hardware was 3 triple redundant computers. So we're talking like it has to work. And if one of them fails, the other one has to work. And if that one fails, we still have another one, right? Like there's a ton more redundancy built in because there are people's lives on the line. And so that ratchets up that whole and just everything. You have to really make sure that nothing goes wrong. And if it does go wrong, you have 2 more safety nets built in.
That's pretty complicated stuff. I don't know how you guys think about that.
Yeah, I have not. I haven't done a lot with that yet, so maybe in the future.
So back to the testing. You said you put it in some kind of a chamber and remove all the air and heat it up. How does that? How do you heat something up? Because I'm sure you're testing for the sun, right? And that's going to be pretty hot.
Right. Yeah.
How do you get that temperature differential?
They use liquid nitrogen actually, and they are able to. I don't know all of the physics and science behind all that, but they are able to ratchet that temperature way up and way cold. And they use liquid nitrogen. We have these large liquid nitrogen tanks outside of the building, and they're getting, when we're doing thermal vac, they're getting filled like every other day, and that's how they do it.
Wow.
Yeah.
And you guys have like a whole, I don't know, is it like a room size? Like the whole spacecraft's the size of like a small car, right?
It is, yeah. So the chamber, just think about a giant chamber around that spacecraft. Yeah, and like I don't know if you've seen any of the JWST photos of it being in that vacuum chamber.
I have not.
They had some photos that they were posting, and I think the chamber's down in Houston, but it's massive because JWST is huge, and they just have this huge chamber, and like you see this massive chamber, and then you see this little tiny guy in the corner, and you're like, man.
I know what you're talking about now. I've actually been there. I didn't know what the the acronym JWST was, but in Johnson Space Center.
Yeah, James Webb Space Telescope.
Yeah. Sorry. Yes.
Yep.
The telescope that has yet to launch, unfortunately.
Correct. Yeah. Yeah.
Cannot wait for that thing to come online. We get to see all of the stars.
Those photos are going to be awesome. I can't wait.
Yeah, it's like what, 20-something meters? Like that's feet, 20. I don't know. It's a huge telescope.
I forget what it is. Yeah, they're big.
I think Hubble's 1.6 meters.
Yeah, that sounds right. Yeah, this one's much bigger. They built all those mirrors at Ball, and I had just started working there when they were starting to ship them out, and they're huge.
These things have to be precise, huh?
Very precise. Yes. Yeah. Otherwise, you'll end up with that Hubble issue they had. You don't want that.
Like the difference was like the thickness of a human hair.
Yeah. Yeah.
How do you even test for that?
It's, again, smarter people than me.
We all have our own spots that we stick ourselves in.
Yep.
Yeah. Well, that was kind of all the questions I had prepared here. We kind of went through those quickly. Is there anything else you'd like to mention before we close this one up?
No, just, again, thanks for having me on. I love talking about all this stuff. This space is just one of those cool industries, and I'm glad that we keep pushing forward with it. And, love watching SpaceX do what they do, and hopefully Blue Origin starts launching some stuff. And it's just a fun industry to follow. It's a fun industry to work in, and spacecraft are cool.
They sure are. Well, thank you very much for joining us, and thank you, Michael, for sending some time over and setting some time aside and having some fun conversations here. Thank you very much, and I'll see you guys in the stars. I need to get a better outro.